So for this section, we're going to talk about optimization, maximums and minimums for functions of two variables. It's super important for this section that you watch the flipped class video on this topic. First, a lot of the stuff is covered there. It's a fairly long flipped class video. And we'll be a little bit shorter on this than for the flipped class video. So basically, we're mostly going to look at functions. So we'll be looking at like z is equal to f of x, y. So we have two variables here. So let's go ahead and jump into an example. Again, the stuff that we're going to need from this is in the flipped class video, so make sure you go and check that out. So let's find the local max, min, and saddle points for z equals f of x, y, and we'll take our function here to be x squared y plus 2y squared minus 2xy plus 6. Okay, so we know we need to find the partial derivatives of this, so let's start by doing that. So f sub x is going to be 2xy minus 2y, and f sub y is going to be x squared plus 4y minus 2x. And now to find our critical points, we want, since these are both defined everywhere, we want where they're both equal to 0. So if we look at the first equation, that would tell us we want 2xy minus 2y is equal to 0. So let's work with this. So this tells me this means 2xy is equal to 2y. No equals 0 anymore, is equal to 2y. So I can cancel the 2's, and this says xy is equal to y. Now this leads to two cases. We have to be a little bit careful. We could have either if y is not equal to 0, then I can cancel the y, and that gives x is equal to 1. The other possibility is y is equal to 0, and then that doesn't tell us anything about x. So those are the two possibilities I get for when this partial derivative is equal to 0. Now let's look at the other one. So the x squared. So now let's look at this one. So I want x squared plus 4y minus 2x is equal to 0. And now this is where we're going to use. So we're going to use these equations down here to plug into this. So I have x squared plus 4y minus 2x is equal to 0. And I break into two cases here. So the first one, let's say if y is equal to 0, so that corresponds to this case. Well, that would mean x squared minus 2x is equal to 0. And this is equivalent to x times x minus 2 is equal to 0. So this leads to x is equal to 0 or x is equal to 2. So the points we get out of this that could be local maximums and local minimums are 0, 0, or 2, 0. So we're going to want to keep track of those. And now the other case is when y is not 0 and x is equal to 1. So this is when x is equal to 1, y is not 0. So let's see what we get from that. So I get 1 squared plus 4y minus 2 is equal to 0. So this gives me y is equal to 1/4. So that gives me the additional point 1/4. So that means my critical points, these are given by 0, 0, 2, 0, and 1/4. And now I need to check whether these are local mins, or saddle points. So we do that with the second derivative test. So we have to take all of the second derivatives. So the second derivative of f sub x is just going to be 2y. The second derivative of f with respect to y is going to be 4, and then f sub xy is 2x minus 2. So that means our discriminant here, dxy, is, remember we fill this in, this is 2y, 4, 4, oops, no, 4 should go on, 4s are the y, so the 4 goes here, and then this is 2x minus 2, and this is 2x minus 2. So that's this times this, so 2y times 4 minus the diagonals times each other, so 2x minus 2 squared. So this is 8y minus 2x minus 2 squared. And so now we just evaluate this function at our critical points. So if I plug in 0 for this, I get minus 4. So that tells me we have a saddle point at 0, 0. If I plug in 2, 0, I get minus 4. So I have another saddle point. And then finally, if I plug in 1, 1/4, I get 8 times 1/4 minus 0 squared. So this is 2. So that means we have a maximum, this means local max or min. So then we look back at the second derivative with respect to x at this point, and this is 1/2, which is bigger than 0. So just like in the one variable case, this gives me a local min. Okay, so for our next example, let's go ahead and do an application of how we might use this to do something useful. So what we're going to do is we're going to look at least squares linear regression. So if you've had a statistics class, you may have seen this already where you're probably just given the formula, but we're going to show how you get that formula here. So let's suppose we've collected data. Right, so we have some points of data here for something we're looking at. And if we graph this data in the xy plane, so maybe we have some points like this, and these are our data. So this could be like x1, y1 here, and maybe this is x2, y2, and so on. And so we'd like to model this data with some function, and for this case we're going to actually choose to make this simple to work with is a linear function. So we're going to pick a line that kind of best fits the data. So it might go through some of the points, it might not go through any of the points, but it's going to best fit the data. So let's say this is y equals mx plus b. And how we're going to measure this is we're going to measure that we want to minimize the squares of the distance. So when I look at this, I'm going to say for each one of these points, I have some distance here that's kind of the error from what I measured to what the line would give me. Okay, so we want to minimize the sum of the squares of these distances. Right, so think of each of those green distances as the error, and we want to square those because we don't want the error here to somehow cancel the error there. They're both errors, so we square them so they're always positive so we don't get any weird cancellation. Because we wouldn't want to think a line that is somewhere the same distance below one point as it is above another point is a perfect fit. It's not. It wouldn't go through either of the points. Okay, so let's go ahead and see how to do this with a particular example rather than doing the most general case. So let's suppose we have and it's really not that much more difficult to do the general case, but just messier notation-wise. Okay, so here is our data points. And now what I want to do is we want to fit these lines So let's draw a picture of what's going on here. So the first data point is here, 1, 1, and then I've got 2, 1 here, and then I've got 3, 3 up here. So what I want is some line that's going to somehow go as close as possible to this. This is my y equals mx plus b. And so now thinking back to what we were saying for our errors, is we want to look at the squares of these distances. So this value right here, this is the value y when x is equal to 3, so this would be 3m plus b. So this distance here would be the square of this distance would be 3 minus 3m plus b squared. And similarly for this one, we could say this is 2m plus b. So this distance, since we squared, the sign doesn't matter, so I could say this is 2 minus 2m plus b, entire thing squared, and so on for the other one. And now what we want to do is we want to choose the m and the b that minimizes this sum. So let's set my function of two variables here, m and b, to be this value. So I guess maybe put this one in here as well, just so we have it. So this is m plus b. So this distance is 1 minus m plus b squared. So we can set this as 1 minus m plus b squared plus 2 minus 2m plus b squared plus 3 minus 3m plus b squared. So that's the sum of the squares of that distance, and we want to choose and b that minimize f of mb, because that's minimizing the errors, picking our line so that it minimizes the error here. So we're going to use what we've done so far to do this. So we take the partial derivatives. So one thing to note, just maybe to make the signs work out a little bit better, is this is the same thing as m plus b minus 1 squared plus 2m plus b minus 2 squared plus 3m plus b minus 3 squared. Because notice the difference between these two things is a -1, and when you square the -1, it goes away. So let's take the partial derivative here with respect to m. So I'm going to have 2, and then I'm going to have m plus b minus 1, now to the first power, times the derivative of what's inside, which is 1, plus 2, and then I'm going to have 2m plus b minus 2 to the first power, and now the derivative of what's inside is 2. And then same thing for the last one, times 3. And if we work all this out and simplify this, this gives me 12b plus 28m minus 24. And now do the same thing for b. So this is going to give me 2m plus b minus 1. And then for this one, that's just times 1 plus 2 times 2m plus b minus 2. And again, we just have a 1 because the coefficient of b is 1 plus 2 is 3m plus b minus 3. And if we simplify this, we get 6b plus 12m minus 10. And now both of these are defined everywhere. So what we want to do is we want to figure out when they're both 0. So we want f of m equals f of b equals 0. So we can set this up as linear equations here and say this is 12b plus 28m minus 24. And this one is 0 is equal to 6b plus 12m minus 10. And now if we multiply this bottom one by negative 2, this will give me, and on the bottom I'll get negative 12b minus 24m minus 20. And now we add those two together, and I get 0. The 12b's cancel off, so I just get 4m. And then I get minus 4. So that gives me m is equal to 1. And then I can plug back into either equation to get what I need. So I get 0 is equal to 6b plus 12 times 1 minus 10. So simplifying this gives b is equal to minus 1/3. So what we've come up with is we think the line should be x minus 1/3. But now we still need to check this gives a minimum for f. So we can go ahead and do that by taking, remember we have these partial derivatives right here, so we just take the partial derivatives of those for our second derivative test. So this is 28. So we check our point, and this is 28, 12, 12, 6. So this is 28 times 6 minus 12 squared, which is 24, which is bigger than 0. And then notice since the second derivative with respect to m twice is bigger than 0, we get that this gives a min. So 1 minus 1/3 gives a min. And our line x minus 1/3 is the line, is the best fit line. So like I said, you can come up with a general formula for this where you have any number of points, and it's not really any more difficult, it's just messier, but it follows the exact same procedure that we just did. And so if you've seen this in statistics class, or you see it in statistics class in the future, that's where this comes from. It's just this max-min problem with two variables. Okay, let's try another word problem. Okay, so we want to find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate planes and 1 vertex on the plane x plus 2y plus 3z equals 6. So if we're thinking of this in terms of a picture here, so I want my box to have faces in the coordinate planes. So there's one, there's another one, that's going to come down here somewhere, like this. And then this point should be on this plane here, so whatever that plane looks like, this point should satisfy x plus 2y plus 3z equals 6. That's the plane it should be on. So if we think in terms of solving this for x is 6 minus 2y minus 3z. So this point here could be the point 6 minus 2y minus 3z, yz. Okay, so now let's set up an equation for the volume of this box. So I know this is x, this is y, and this is z. So the volume is x times y times z. But notice this point over here is telling us the x in terms of the others. So I can say v of just 2 variables, y, z, and then we can replace that x with our requirement that be on the plane, and then times y and z. And so now this gives us the volume in terms of 2 variables, which we know how to work with. And now we want to maximize this volume here. So just like we've been doing, we take the partial derivatives. So this is going to be 6z minus 4yz minus 3z squared. And we can factor this as, we can factor a z out of this and get 6 minus 4y minus 3z. And then we can do the same thing with the partial with respect to z. And for this, I can again factor out a y. And I get 6 minus 2y minus 6z. And so now we want where both of these are equal to 0. And one thing to note here is, so if we look at v of y, so this is equal to 0 when z is equal to 0, or when 6 minus 4y minus 3z is equal to 0. And now the first case here, this leads to a volume equals 0. So that's probably not going to be our maximum possible volume. And same thing if we do v of z, this is equal to 0 when y is equal to 0, which again leads to a volume of 0, or when 6 minus 2y minus 6z is equal to 0. So we're really going to want to focus on these two here, because those should give us a non-zero volume. As long as you get something other than 0 for this, bigger than 0, then the first two cases are not what we need. So if we take these and we solve these and bring the 6 to the other side, I would have, for the first one, 6 is equal to 4y plus 3z. And for the second one, I have 6 is equal to 2y plus 6z. So I can multiply this one by minus 2, and I'll have 6 is equal to 4y plus 3z, and then I'll have minus 12 is equal to minus 4y minus 12z. And so now add those two equations together, and I get minus 6 is equal to minus 9z. So z is equal to 2/3. And then we can plug that back in to solve for y. So y is equal to, say, 6 minus 3z over 6, just solving this equation up here for y. And so this gives me 6 minus 3 times 2/3. Oh, this should be over 4, not 6, sorry. Over 4, so this is equal to 1. And then we can go back to the beginning and remember this x is 6. So this is 2. So the volume for this measurement is the product of all of these. So this is 2 times 1 times 2/3, which is 4/3. This tells us we can get a positive volume, so it was fine to ignore those two up here that were giving this 0 volume. And now we just need to check this is actually a maximum. This is yz. So d of yz is minus 4z. 6 minus 6z, 6 minus 6z, minus 6y, which is 24yz minus 6 minus 6z squared. So if I look at the values I have of 1 and 2/3, this gives me 16 minus 4, which is 12, which is bigger than 0. And then v of yy at 1 2/3 is equal to minus 8/3, which is less than 0. So this gives me a local max. Okay, so we see these are similar to the max-min problems we did with one variable. We have a little bit more to do here, but again, we're finding critical points in this case because we're going to have two variables and then using a second derivative test to check maximums and minimums. But otherwise, it's pretty much the same setup.